Hello students! So we are moving on to our next big topic, oscillations. So let's get started. Anything that moves back and forth, regularly is vibrating. So if I do this, my hand is vibrating. Now, something that naturally tends to go back and forth is called an oscillator. So for example, if I have a ball at the end of a string, it would, if you disturb it, it'll swing back and forth, and so it's an oscillator. Now, this type of oscillator is called a pendulum. Now, a counterexample would be a loudspeaker. Loudspeakers, they vibrate, they go back and forth, but they don't do it naturally. They are being driven by an amplifier. So although loudspeakers do vibrate, we don't call them oscillators because they don't do it, on their own. Whereas a pendulum, once you get it going, it just keeps going back and forth on its own. Okay. Now, the time it takes for an oscillator to go back and forth is called the period, and it gets the symbol capital T. And you can calculate it for a pendulum. Here is the formula. It's 2 pi times the square root of the length of the pendulum. So from here to here, that's the length. And so it's the length divided by by g, which is 9.8, or more accurately, 9.81. Here is an example of doing the math. Let's say we have a grandfather clock, one of the great big clocks, and its pendulum is 1 meter long. So now, the pendulum in a grandfather clock, here's the weight, and it's the pivot point is somewhere up here, and there is a rod connecting the weight to the pivot point, and it will swing back and forth. So the period is the time it takes to go there one way and then back the other way. That's one full period. And so here's the math. So you have 2 pi times the square root. The length is 1 meter. You're dividing by 9.8. I should have put 9.81, but anyhow. And you get an answer, 2.07 seconds. Okay. So let's do a problem. I have a clock that's right over there, and its pendulum length is, I just measured it, 25 centimeters. I want you to calculate the period of this clock. All right. Okay, students, so you did the math, right? What did you get? Write it down. And now this clock, its pendulum, goes from a little bit above the Seiko brand here and down to right about here, right? This is the pendulum, and the pivot point is right above the Seiko thing, and so that's 25 centimeters. Now I've got a stopwatch, and we'll see whether or not you got the right answer. What I'm going to do is I'm going to time the time for 10 swings, and then we'll divide by 10, and that'll be the period for one swing. All right? So when you do something like this, you want to start with 0, right? So it's going to be 0, 1, 2, and then when we get to 10, that's when we stop. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, our answer is right here. It's 9.989 seconds. Whoa! So that's basically 10 seconds. 10 divided by 10, right, because it was 10 swings, is 1. Hopefully your answer was 1 second. If you didn't get 1 second, then stop and figure out what you did wrong. So that was an example of a pendulum oscillator. Now let's take a look at the next kind we're going to be studying, and that is spring oscillators. So a spring oscillator is a mass on a spring. And I'm going to show you an example here. This is one of the PhET simulations. And here I am putting a 100-gram mass on a simulated spring, a simulated mass on a simulated spring. Here I'm putting a 250-gram mass on the simulated spring. Notice that the period is different between the two. So to calculate the period, here is the formula. It's 2 pi times the square root of the mass divided by the spring constant. Or sometimes I call it the spring stiffness. Notice that unlike the pendulum case, this formula doesn't involve G. So a spring oscillator doesn't care what planet you're on. It'll always have the same period. Here's an example. If you had a 1 kilogram mass, if your spring stiffness was 100 newtons per meter, then you would have a period of 0.62 seconds. So here's this clock which has a spring oscillator in it. Here you're seeing the front side of it, but now I'm going to show you the spring oscillator, which is on the back side of the clock. And if I bring the clock close up, I think you can see that there is a little wheel that's going back and forth, turning clockwise, counterclockwise, and it's bouncing back and forth because of a spring which is wound around the rotation axis. So this is a slightly different spring oscillator. It doesn't bounce up and down like the previous example. Instead, it's a wheel, and instead of the mass mattering, it's the moment of inertia. So the moment of inertia is acting like the mass, but you still have a spring, and it's bouncing left and right, clockwise and counterclockwise. So far, we've been talking about the period of our oscillators. But there's another way of looking at the timing of oscillators, and that is in terms of frequency. Frequency, which gets the symbol F, is the rate at which your oscillator is going back and forth. The units of frequency are cycles per second. So a cycle is the fact of going back and forth and back to where you started from. That's a full cycle. So frequencies in cycles per second. And about 50 years ago, the unit of cycles per second was renamed the Hertz in honor of the German physicist Hertz, who built the first radio transmitter and receiver. Now, the cycles part of Hertz are phantom units. That's what I meant. That's what I call units that will disappear on you when you're doing homework problems. They're just like radians will disappear and revolutions will disappear. These are units which can come and go, and so don't let that bother you. Okay. Yeah. Now, the abbreviation for hertz, instead of writing out Hertz, we abbreviate that Hz. Now, frequency and the period, the frequency of an oscillator and its period, are related very simply by reciprocals. So the frequency is the reciprocal of the period, and the period is the reciprocal of the frequency. So as a really simple example, imagine that you have a jackhammer hitting the ground 20 times per second. Well, the frequency is going to be 20 hertz because that's... Huh?
Someone looked at it.
No, that was me. So the jackhammer is hitting the ground 20 times per second, and we hear a sound at 20 hertz. And the period of that sound is each pounding sound that you hear is separated by 0.05 seconds. So the frequency is 20 hertz. The period of that sound is 0.05 seconds. Now, we need to introduce another kind of frequency. It's omega. Now, we've seen omega as the rate of rotation of like a wheel, and it's in radians per second. And omega is going to we're going to call it angular frequency, and it has the same units, radians per second. And we're going to see that we'll see how this comes about in a little bit. The angular frequency omega is equal to 2 pi times the regular frequency f, and since f is 1 over t, omega is 2 pi divided by the period. For this example here, the angular frequency of the sound that you were hearing from the jackhammer would have been 2 pi times 20 hertz, or 126 radians per second. Okay, now here is a vocabulary word, harmonic motion. So we've been talking about our oscillators, like the pendulum oscillator swinging back and forth, or the spring oscillator bouncing up and down. Those are harmonic oscillators. They do harmonic motion. And so here's an example in this picture. You have a pendulum. Here is the bottom end, the mass of the pendulum, and here is a string, and it's attached to the ceiling, maybe here. And the person doing the demonstration here has let the pendulum go back and and it's now moving back and forth like this. It's going back and forth, swinging back and forth. Now, this particular pendulum has sand in it, and the sand is flowing down onto a conveyor belt. I think this is just paper on a roll, but it's like a supermarket conveyor belt. And so the paper is moving this way, and as the pendulum goes back and forth, you can see that it's drawing out a sinusoidal waveform here. You could call it a sine wave, or you could call it a cosine wave, but either way, we call it a sinusoid. And this shape here is called a sinusoidal waveform. I'd like to show you another example of an oscillator and sinusoidal motion. The device up here at the top is an electronic oscillator. Inside, there's a circuit which has the electronic equivalent of a spring and the electronic equivalent of a mass, and inside, the electricity is bouncing back and forth, and the oscillating voltage, you get an oscillating voltage that comes out of this connector here, and I've got it connected by a cable to this thing called an oscilloscope. The job of the oscilloscope is to tell you what the voltage is on this wire. When the voltage is high, the dot goes up. When the voltage is 0, it's at the midpoint. When the voltage is negative, it goes down. So as you can see, it's bouncing up and down. Sometimes it's positive, sometimes negative, and so on. Right now, I have the oscillator set to 1 hertz, 1 cycle per second. So you can see that it goes up and down. The time it takes to go up and down is 1 second. The reciprocal of 1 second is 1 hertz. Now this is sinusoidal motion. Now the next thing I want to show you is how this can become a sinusoidal wave form. Right now the dot is just moving up and down, but I can also make this thing, the dot, move to the right linearly at a constant rate. So the time it takes, it won't be accelerating. It'll be going at a steady rate to the right. It'll also be going up and down. So let's make that happen. So it's, as you can see, it's starting to move to the right. And I'm making now go faster. You can just barely see that the phosphor of the screen makes like a line that's trailing behind the dot. And you can just barely make out the sinusoidal shape. I'm going to make it go faster, and you're going to see it more clearly. So let's increase the speed of oscillation. I'm going to make it be 10 times higher. So now it's going up and down at 10 cycles per second, 10 hertz. I can now increase the speed going to the right, and you can see more clearly that it does look like a sine wave. Now, while we're doing this, let's have some fun. Let's make it go 10 times faster. Okay, so now it's going up and down at 100 hertz. I can make the speed of this thing going to the right faster, and it still looks like a sine wave. Let's make it be 1,000 hertz. It's going up and down 1,000 times per second. How high can we go? Well, according to this thing up here, it says 20 megahertz. So this oscillator can make the dot go up and down 20 million times per second. And this thing can go back and forth a few million times per second as well. So these electronic oscillators are very fast.